Okay, now let's talk about the anode. So this is the positive part of the X-ray tube, or positive side. In diagnostic X-ray imaging, we use rotating anodes. So you'll see in the book they talk about stationary anodes, but I won't talk about that here because in X-ray we always use the rotating ones. So the anode has a few main jobs. One of them is to conduct electricity, so basically handle electrons. And that can include conducting those excess electrons back through connecting cables back to the high voltage generator. So sometimes what that anode does is it actually manages any of those excess electrons instead of converting all of them to X-rays. The anode also radiates X-rays through the interaction of the cathode electrons and then the tungsten rhenium, which is part of the anode target. And then it handles a massive amount of heat generated by the X-ray process. And it does that because it has a little bit extra surface area. So while the electrons will be hitting one part of the actual anode, this whole surface area is able to kind of dissipate and handle the heat produced by the process. Also, through the use of rotation, so that not just one single area is bombarded by those electrons the whole time, as in the stationary anode. Again, surface area, the bigger the diameter, the wider it is basically, the more area for heat dissipation. And then the copper, molybdenum, and graphite under the tungsten also help manage heat. So the rotor and stator we touched on briefly when we were talking about mutual induction. There's no physical connection between the rotor and the stator. Instead, what happens is the stator has these windings they show you here. What happens is the pairs of windings, so for example this one and this one over here, pairs of windings will energize. And basically what that means is they'll start to act kind of like a primary side of a transformer. And what they're going to do is they're going to induce energy into the rotor. Now what the rotor is going to want to do is line up with these pairs of stator windings. And then just as it rotates to align parts of its components with this pair here, those will shut off and we'll get an energization of another pair of windings here. So the rotor will turn, trying to line up with this pair, and so on. Now granted, this all happens in a split second, and we're talking about it over the course of a couple minutes, so bear in mind that it's a pretty fast process of energizing, and that rotor's just trying to keep up with those energizing pairs. Further on the anode, we have something called a line focus principle. And believe it or not, this principle is why we have an angle on the anode at all. So if there's an angle, what we can have is a large actual focal spot. You can see it here. It's kind of the width of this beam size here in this picture. We can have it a little bit wider here, but still a small effective focal spot. So what that means is we have a little bit more heat management by making our beam size a little wider, our actual focal spot a little bit wider, better heat handling, but we can still have a smaller focal spot, which means we get better spatial resolution. Remember, the wider the spot, the less detail you're going to get. Now we can't change this angle, but we can change our focal spot depending on what our needs are. And the angle of this anode that creates this whole kind of process here is usually between 5 and 20 degrees in any given X-ray tube. I did give you a little analogy here. If you were standing on one side and pointing a flashlight at your friend, and your friend held up a hand mirror at that flashlight, and then they started to tilt it downward, you'd see that at first you have just a little bit of light deflected on the ground. And then as they angled it it probably got wider and wider until the lights just stopped hitting the hand mirror at all. All right, now the anode heel effect. So the angle that we were just talking about allows for pretty good spatial resolution and better heat handling, but it also kind of means that X-rays get emitted at different energies from the anode target. So if a cathode electron hits this target closer to the anode side, so closer to this side over here, what it means is, and they kind of show you here through this illustration, it might go through more interactions with that target. It'll still come out as an X-ray, but again, it went through a little more interactions to get where it's going. What that means is we have an overall kind of weaker radiation intensity on the anode side than over here on the cathode side, where an electron maybe hit the anode target and we have an X-ray that does nothing but head toward the patient. No interaction, more interaction with the anode there. Now the difference in strength between this cathode side of the beam and the anode side can be about 45%, so a pretty big range there. And that's where we get fat cat, that you all may remember from last semester, where if at all possible you want to put the thicker side of the body toward the cathode side, because we do have up to 45% stronger X-rays on that side. Finally, off-focus radiation. The X-ray production process isn't perfect, so sometimes those electrons, they could bounce away from the focal spot, and that's what they're kind of trying to show you here. And they might cause X-rays from different areas of the target, called extrafocal X-rays. All these do would cause fog or maybe increase skin dose, so a diaphragm near the exit window and a metal enclosure help kind of keep these at bay.